we will find out the quantization, signal to quantization noise ratio. Okay, signal to quantization noise ratio. Fine. Signal to generally நம்ம signal to noise ratio ன்னு சொல்லுவோம். Here noise is due to the process of quantization. So that's why this is signal to quantization noise ratio, SQNR. இப்போ இதுக்கு நம்ம ஒரு practical values எதனா எடுத்தாகணும். Signal, say I am having some signal x of t. X of t is am sin omega t or cos omega t. Am sin omega t is the analog signal that I want to convert the signal into digital data. So I want to find out signal power as well as the noise power. You know what is the signal power of this signal? That is simply am square divided by 2. This is the signal power, common formula. Then I want to find out what is the noise formula, noise power. You do not know what is the nature of the noise, but you know one thing, noise distribution. You know noise distribution. Say the quantization error can vary from minus del by 2 to plus del by 2. Already we have identified this. What is the minimum quantization error? Minus del by 2. Otherwise, magnitude wise del by 2. The range is from minus del by 2 to plus del by 2. That will have uniform distribution. Uniform distribution. Then once if it is uniform, what is the y-axis value? That is 1 by del. So this is the distribution, probability density distribution for quantization error. So FQE, then QE, probability PDF. So the quantization noise nature I have given in terms of PDF, probability density function. Then I have to find out what is the power of this distribution. Already I know to calculate the power, I will be using this formula, E of x square formula. But here, instead of x square, I am having QE, quantization error square formula. So now I want to apply this formula. What is E of QE square? So that is integration. Again, limit goes from minus del by 2 to plus del by 2. Then x square into f of x. So this is f of QE. Then instead of dx, I will have dQE. Now I know what is the distribution value. That is 1 by del. That is 1 by del. So here no x. Here you will not get any x. Now I know what is the f of q. That is 1 by del. That is 1 by del. So I'll substitute that value. Minus del by 2 to plus del by 2. QE square. This is 1 by del. Then dq. So now QE square 1 by del you can take out, because this integration is with respect to q. Then if you do the integration, QE cube divided by 3, then apply the limit del by 2 minus del by 2. Once if you solve this, just instead of q you apply del by 2. That's it. Finally, you will get del square by 12. Okay, again, with the help of simple formula, we can write. We know for uniform distribution, what is the formula? BA square divided by 12. In our case, what is B? Del by 2. What is A? Minus del by 2. So this is plus del by 2 divided by 12 whole square. So that is del square by 12. So this is quantization noise power. Okay, so now I have derived quantization noise power. That is del square divided by 12. Already I know what is the signal power. Then I and also know the quantization power, quantization noise power. That is del square divided by 12. Now I want to calculate the ratio between these two. Before that, we'll calculate what is del, step size. So step size del I have defined like dynamic range, that is V max minus V minimum divided by 2. V max minus V minimum divided by 2. For the given signal, sinusoidal signal, what is the maximum value? AM. AM is the maximum value, minus of minimum value is the minus AM divided by, it is not 2, that is number of level. Okay, that is number of level. Again, number of level is 2 power n. So this is 2 times of am divided by 2 power n. Okay. So now I have represented del in terms of the actual value, in terms of maximum amplitude and the number of bits. Now I'll try to find out signal to quantization noise ratio. That means signal power divided by noise power. Already I have calculated the signal power, that is am square divided by 2. Now noise power is del square divided by 12. Del I have already calculated. This is del. So 2 times of am divided by 2 power n whole square divided by 12. So now if you solve this carefully, a very simple mathematics, if you solve this, finally you will get 3 by 2, 2 power of 2 power of 2 power n, or may not be, it's like this, 2 to the power of 2 power n, 3 by 2, 2 to the power of 2 power n. Now the question here is, okay, see, ultimately I got some answer, signal to quantization noise ratio. Just you apply this formula, or otherwise can I try? Say I'll try. Yeah. So this is am square divided by 2. This 12 will go up. This 12 will go up. Then 4 times of am square. Then 2 power n. 2 power n whole square. 2 power n whole square. 2 power n whole square. So am square cancel. 2 means 6 to 3 by 2. This 2 power n whole square will go upwards. So 3 by 2, 2 power n whole power 2, 2 power n whole power 2. So now, what is the 3 by 2? 3 by 2. Can I write this as 2 to the power of, can I interchange this 2 and n? 2 to the power of 2 power n. In some book, they might have given like this, 2 to the power of 2 power n, 2 to the power of 2 power n. So once if you take the logarithmic value, once if you represented this in terms of dB, signal to quantization noise ratio in terms of dB, then the final answer here is 1.86n, 1.86n, then dB. 10 log formula apply பண்ணனும் இங்க இருக்கிற நம்பருக்கு n எதுவும் பண்ண முடியாது, so அது வந்து 6n ன்னு வரும். Then again I can write the modified version of this. Say this is 3 by 2. I can a power m whole power n formula, 2 to the power of 2n also, 2 to the power of 2n. Please verify this. All are correct or wrong. You take some number for n, some random number, different number, just to verify it. All the expressions are correct or not. Okay, if it is correct, then SQ1R in dB, I can write like this, 1.8 plus 6n dB. Now, what is the observation here? I know when I increase n, clarity will increase. That means when I increase n, here itself, it is indicating SQ1R is increasing. Signal to noise ratio. ஏற்கனவே சொல்லியிருக்கேன், signal to noise ratio increase ஆச்சுன்னா நம்மளுடைய communication வந்து பெட்டரா இருக்கும். Why it is increasing? Because I know when n is increasing, definitely quantization noise will reduce. So once quantization noise reduces means definitely signal to quantization noise ratio will increase. அதுதான் வந்து நம்ம ஃபைனல் எக்ஸ்பிரஷன்லயே அதான் பார்க்குறோம். இப்படி இன்க்ரீஸ் ஆகுது. Now what is observation? Suppose if I'm increasing n by 1 bit, then SQNR will increase by 6 dB in terms of dB. See, when I put n is equal to 1, this is 6 dB plus 1.8. If it is 2, 12 dB. So for every 1 bit increase, the signal to quantization noise ratio increases by 6 dB, or otherwise in terms of number, it increases by 4 times. 4 times. Here you can observe. When you put n is equal to 1, this will give 4. When you give n is equal to 2, this will give 16. Anyway, this is constant. 16. That means for every 1 bit increase, in terms of number, it increased by 4 times. In terms of dB, it increased by 6 dB. Or otherwise, if you have doubt, you take 10 log of 4, that will give 6 dB. Okay, so either it increases by 4 times or it increases by 6 dB. That is the important observation from here. Important observations from here. So that வந்து நம்ம இன்னைக்கு ஸ்டாப் பண்ணுவோம். We started with the PCM pulse code, sorry, startingல நம்ம problem solve பண்ணோம். Then we started with PCM pulse code modulation. அதுல different block இதெல்லாம் வந்து பார்த்தோம். Sampler, quantizer, then encoder. Encoder means assigning level to bit assignment. Encoding means level to bits assignment. ஒவ்வொரு லெவலுக்கும் bits assignment தான் வந்து encoder. Then basics இதெல்லாம் பார்த்தோம். How to fix fs, minimum fs என்னவா இருக்கணும். Then what is the relation between fs and ts, இதெல்லாம் பார்த்தோம். Then next we have defined step size. Okay, step size depends on the number of level and then dynamic range. Then we have seen the quantization error. Maximum என்ன quantization வர chance இருக்கு. Okay, the maximum quantization error is related to the step size. That means del divided by 2. Then what is the overall bit rate? That is RB is equal to n times of fs. Then we have seen the units relation. Then to transmit this signal over a particular channel, we need some bandwidth, that is half of the bit rate. In some other time, if you use raised cosine filter concept, we have to use this formula where alpha will vary from 0 to 1. So bandwidth, we can also write like 1 plus alpha divided by 2 TB. அதுக்கப்புறம் சேனல் பேண்ட்வித்துக்கும் யூசர் பேண்ட்வித்துக்கும் என்ன ரிலேஷன் பார்த்தோம். when we increase RB, user bandwidth will increase so that you cannot accommodate more number of user. That is the major problem. But once if you increase RB means either you may be increasing N or Fs. That means indirectly you will be increasing the clarity. Okay, clarity. You are increasing clarity means quantization error will be decreasing. Quantization error will be decreasing, but you cannot accommodate more number of people. அதுக்கு ஒரு எக்ஸாம்பிள், ரியல் டைம் எக்ஸாம்பிள் சொன்னா. தென் சிக்னல் டு குவான்டைசேஷன் நாய்ஸ் ரேஷியோ என்னன்றதை கண்டுபிடிக்கணும். ஐ ஹவ் டேக்கன் யூஷுவல் சிக்னல், ஆர்டினரி சிக்னல், சைன் சிக்னல். ஃபார் தட் திஸ் இஸ் த பவர். தென் நாய்ஸ் இஸ் மீன்ஸ் ஹியர் quantization noise. I know the nature of the quantization noise, that is uniform, and also it goes from minus del by 2 plus del by 2. Then using the formula from the random process, I can calculate the power of the quantization error, quantization noise power, that is del square by 2. Either you can do the derivation or you can remember the uniform distribution formula. From that also you can calculate del square by 12. Then del I am representing in terms of amplitude and then step, number of steps, number of bits. Then once if you do the mathematical adjustment, finally you will be getting expression like this, different expression, all are same. Then finally I'm writing this SQNR in terms of dB, so 1.8 plus 6n. So for every 1 bit increase, the signal to quantization noise ratio will increase because noise will decrease. That means quantization noise will decrease. So finally for every 1 bit increase, SQNR increases by 6 dB, or it is in terms of number. If you are representing in terms of number, it will increase by 4 times. This is the final observation. Again, at the receiver side, say finally we have converted in terms of bits. Somehow we have converted in terms of bits. Mostly in our example, each sample we have assigned into 2 bits. Each sample we have assigned into 2 bits. Now based on this bits, okay, I have to form the levels. Say I will get diagram like this with help of the level. We are at the receiver side. So first I have to decode this. Okay, from the bits at the receiver side, I have to form the digital diagram, digital signal. So now I will get in terms of levels. Then from the levels, I have to get the exact shape. So first of all, after receiving the bits, you have to decode it. Then you have to pass it through a dequantizer. So decoding means assigning levels. After assigning levels, okay, that has to be converted into the diagram. So that will be done with help of the dequantizer. Then finally, from the step diagram, we have to get the actual original signal. So here we will be using low pass filter. Okay, at this point, this may not be very evident how we are getting exact output from the step diagram with the help of the low pass filter. In future, if time is there, I will explain this. So at the receiver side, we are using decoding. This is the receiver side. At the receiver side, we are using decoding, then dequantization, then low pass filter. At the output of the low pass filter will be the analog signal, original analog signal. Here, this low pass filter will do the smoothing operation. That means here the diagram will be something like this with help of the steps. So that discontinuities will be removed by low pass filter. You know the properties of low pass filter. It will allow only low frequency, but at the place of discontinuities, it will produce very high frequencies. Maybe you might have studied in the signal system. So automatically that high frequencies will be removed by low pass filter. Then finally you'll get the smooth output that will be the original analog signal. So இன்னைக்கு இதோட ஸ்டாப் பண்ணுவோம். In the next class we will continue with this next version, that is DPCM delta modulation, then later on digital communication.